Good morning, students. So today we are going to discuss on partial wave analysis, which is very important question as far as this scattering theory of quantum mechanics is concerned. Of course, we learnt about the Born approximation, the scattering theory, the scattering amplitude, and thereby differential cross section. And we applied Born approximation for two models. Yesterday we learnt about two models. This is about coulomb potential and Yukawa potential. Very important thing about Born approximation is we are going to consider only the weak potential. The potential is considered to be very weak. Of course, it is very weak. The potential is very weak. It implies that the kinetic energy will be very large. So it's obviously it's clear. So kinetic energy of the incident particle will be very high. Okay, so we are going to take into account the weak potential for Born approximation, whereas in partial wave analysis we are not going to consider the weak potential. Irrespective of all the potential, this will work out. So potential is weak or strong or medium, whatever may be the potential, this will work out. Partial wave analysis. And we are talking about in Born approximation, we are talking about the incident wave is nothing but a plane wave equation. E power I k r, probably you know, even k equals k naught, e power I k dot r, e power I k r cos theta. So we know about the incident wave, which is nothing but a plane wave equation. But here we are going to consider on in partial analysis, we are going to consider the incident wave is consisting of infinite number of free sphere waves, spherical waves. I repeat, the incident wave consists of free spherical waves. Okay, there of course it was plane wave. Now we are going to consider this this incident wave is nothing but a spherical, infinite number of free spherical waves. Each wave is nothing but a partial wave. So each spherical wave is nothing but a partial wave because it contains lot of angular momentum. So we are going to consider different angular momentum eigenvalues in this equation. All the waves, they will interfere and we will get the scattering waves. So this is the idea behind the partial analysis. I repeat, so the incident wave consists of free spherical waves. This each wave is considered as a partial wave. For example, when you take different angular momentum, for example, L equal to 0. So L equal to 0, L equal to 1, L equal to 2, we will have different angular momentum of waves. And these waves are called S wave, P wave, D wave, F wave and so on. For L equal to 0, we have S wave. For L equal to 1, we have P wave. For L equal to 2, we have D waves. So all those waves will have different angular momentum eigenvalues. And we are going to add all those things. So there will be some interference. So we are going to use these expansion theorem. Okay, this interference of waves is nothing but your scattering waves. So this is the idea. One. Then another main idea is we are going to use the solution of hydrogen atom. So which we already solved, which we have discussed earlier in quantum mechanics 1. The solution of hydrogen atom, which is nothing but the product of radial part and angular parts. We know already. These angular parts, which consist of theta and phi. Together we call this as spherical harmonics. So the wave function, the obtained wave function for the hydrogen atom is nothing but the product of radial function and the spherical harmonics. So we know already. This radial function we are going to solve this radial function as Bessel function, spherical Bessel function, and spherical harmonics as Legendre polynomial. Okay, so this is the idea. So we are going to have the product of both. One is the radial part and another one is spherical harmonics. The solution of radial part will be spherical Bessel function. The solution of spherical harmonics will be Legendre polynomial. The product of Legendre polynomial and spherical Bessel function will be the complete wave function. Is it okay? So complete wave function, the total wave function. This total wave function will be compared with, already we learnt about the equation in the first lecture, which is nothing but the relation between scattering amplitude and a differential cross section. We are going to compare these two and get scattering amplitude. So that's the idea. Okay, so with this introduction, we are going to start with the partial wave analysis. It's very tedious one, but it's very important one. But it contains full of mathematical ideas. So as I said in the introduction, your V of R is very weak in Born approximation. And in fact, the kinetic energy will be of the incident particles will be very large. And it is an approximate solution of differential calculation, we know already, because we used Helmholtz equation, and solution of Helmholtz equation that will give us the Green's function, and thereby we obtain the wave function. So it's nothing but the solution of differential calculation. In this section, there will be no limitation of strength of potential. There won't be weak potential or strong potential, nothing. So it will work out for all the potentials. V of R is taken at account. The angular momentum of the incident particle is conserved. Okay, that is, the particle scattered from the center potential will have same angular momentum before and after collision. Of course, we have to consider only elastic scattering. So before and after collision, the angular momentum is conserved. Let us assume the potential being spherically symmetric. Of course, we know only then we can use spherical polar coordinates. So we are going to have spherical potential symmetry, in which the condition will be V of R vector equals V of R. Irrespective of all the direction, it will be the same. So independent of direction. The wave function in the eigenstates of the angular momentum is expanded. So we are going to expand the eigenstates of angular momentum. Okay, with the definite angular momenta are called as partial. So each wave is nothing but a partial wave. So this will have different angular momenta, L equal to 0, L equal to 1, L equal to 2, S wave, P wave, D wave, and so on. Okay, so we can solve scattering problem for each partial wave separately, and then at the end put together to obtain full scattering amplitude and thereby differential cross section. Assume that the incident particle having plane wave in the direction, as we have done earlier. So your psi incident is nothing but e power I k dot r. Usually we will write as I k naught dot r. But we are going to consider as elastic scattering, so k naught will be replaced by k. So e power I k dot r, which is equal to e power I k r cos theta. One thing you can notice is there is no phi here. Okay, there is no phi here. Correct, because phi is constant. And because we are going to consider only spherical symmetry. So which can be expressed as a linear combination of three spherical waves, and it can be expanded in terms of partial waves. These spherical waves are nothing but partial waves. Now we are going to consider the Schrödinger time independent wave equation for the scattering problem, which is given by this equation under center of mass frame, because we are going to use only the reduced mass mu. So equation is very clear, and this equation represents the scattering problem. Okay, Schrödinger equation for the scattering problem. And of course, where mu is the reduced mass of the projectile and the target particles. We know that the general solution of the above Schrödinger equation is given by this. Look at this equation. We know that wave function, which is nothing but the product of radial part and angular parts. So for example, which we learned already in hydrogen atom in quantum mechanics 1. So which is the product of radial part and angular parts. Okay, so psi is a function of r, theta and phi. Theta and phi together, what we call this as YLM, spherical harmonics. YLM theta comma phi, spherical harmonics. And of course, using expansion theorem, we know that the capital psi is written as expansion coefficient multiplied by small psi. We know already. Okay, expansion coefficient multiplied by small psi, like C1 psi 1 plus C2 psi 2 plus C3 psi 3, which is equal to capital psi. Okay, so summation over L comma M. Summation over L comma M. Okay, and just a substitute here, we will have the wave function exactly like this. So CLM is the expansion coefficient, R is the radial part. Just a substitute here, you will get this complete solution. Just a substitute here. Okay, instead of psi, you just substitute Ry. So you have Ry. See, R KL, Y LM. It depends on KL. It depends on LM. Okay, principal quantum number, orbital quantum number, and magnetic quantum number. So we know already. The wave function is expanded in terms of spherical waves and it is called as partial wave expansion. So partial wave expansion depending on L values. For L equal to 0 we have another m, L equal to 1 we have m. So we can expand. We are going to use these particular results for studying the scattering problem and it leads to partial wave analysis. Okay, is it okay? So now we are going to express the spherical harmonics first, YLM. YLM is given as in terms of Legendre polynomial. The solution of the spherical harmonic we are going to take as Legendre polynomial. So we know already this. We learnt in hydrogen atom itself. I repeat, come on, spherical harmonic, solution of spherical harmonic is nothing but Legendre polynomial. So PLM cos theta. This is CLM coefficient. Okay. What is this 1 by root 2 pi e power I m phi? The solution of your phi. The solution of a phi and 1 divided by 2 pi. For example, if you just take integrate 0 to 2 pi, d phi will give you 1 divided by root 2 pi. Okay. So this is nothing but normalization constant of your phi. Okay. So we learnt already. So that's why we have written as 1 divided by 2 pi CLM PLM of cos theta e to the power I m phi. Of course, we will have to go only with the spherical symmetry. And this is spherical symmetry is nothing but your rotationally invariant. Okay, V of r vector equal to V of r. And as I said earlier, we will have to remove this phi. Okay, phi should be constant. Just now we discussed. So for that, what we are going to do is just substitute m equals 0 here. So m equal to 0, it implies that your m equals 0 means L0. So L0, y L0, theta comma phi is given as PL cos theta. So this becomes PL cos theta, CLM divided by root pi give us AL. Okay, your CLM divided by 1 divided by root 2 pi will give you AL. So this equation, that is the complete equation, I have written as AL R radial part and your angular part will be PL cos theta. Is it okay? Equation 6.96. Is it clear? Come on, I repeat. So this is your complete wave function. Okay. So this is your radial part. This is your angular part. So angular part is taken as Legendre solution of Legendre polynomial. Okay. Now if m equal to 0, this can be written as PL cos theta alone. CLM divided by root 2 pi will give you AL. So the complete solution for this equation can be written as AL radial part and PL cos theta. Is it okay? So I have written same. Now each term for L equal to 0 we can have one expression. For L equal to 1 we have another expression. For L equal to 2 we have another expression. So each wave is nothing but a partial wave. Collection of all the partial waves at the end we are going to get. They will interfere and we will get the scattering waves. So that's the idea. Okay. Now, so we have done for polar angles and azimuthal angles, spherical harmonics. Now we are going to go for radial part. So this is the radial equation which we already learnt in hydrogen atom. So this is for the radial equation from the hydrogen atom. So which is given in terms of angular momentum, angular quantum number. So this is the equation, radial equation. Okay, equation 6.97. The solution of radial function is the superposition of angular momentum eigenstates with a definite angular momentum L, which is given by. So the solution of this is given as this in terms of spherical Bessel function. So your radial part in terms of Bessel function, angular part in terms of Legendre polynomial. So product of these two will give you complete solution. So that's the idea. So your RKL of R which is equal to summation over L equal to 0 I to the power L 2L plus 1 JL KR. So we know about Bessel function, we know already, studied in mathematical physics. Okay. The plane wave is equivalent to the superposition of infinite number of spherical waves. Each individual is nothing but a partial wave. The waves in L equal to 0, 1, 2 are represented respectively as S wave, P wave, D wave. the low energy scattering can be analyzed satisfactorily with the S wave. Of course, for the simplicity, we can go with L equal to 0. We can observe easily S wave. Okay, and the remaining term will be T wave, D wave, and so on. Now we know already about this equation. The total wave function is given as incident wave plus scattered wave. So right from the beginning, we have been learning this one. Okay, the total wave function is nothing but asymptotically, which is nothing but incident wave and the scattered wave. We know already. The incident wave is given as e power ikr, which is equal to e power ikr cos theta, which is equal to this equation we know. Okay, so PL cos theta are the legendary polynomial, and each term on right hand side gives us a spherical waves. Now we are going to substitute in the expression for the incident wave function in equation 6.99. Okay, we are going to substitute. We will get the wave function is equal to, this is replaced by this one, so we have replaced, okay, plus your f of theta comma phi e power ikr by r. Come on, instead of e power ikr, you write this expression and substitute in this equation and get equation 6.101. Is it okay? So this is your incident wave, and this must be your scattered wave. This will be your total wave function. Okay. So in almost all scattering experiments, detectors are located at too far away. We know very large distances from the target that are much larger than the size of the target itself. We know already. Thus, the measurements taken by the detectors related to the scattered wave functions are at large values of r. That's why we are going to use asymptote. The Bessel function JL of kr for large values of r, which is nothing but asymptotically, is given by this expression. Okay. So Bessel function is given as sin kr minus L pi by 2 divided by kr. So we have already learned this one. Okay, we learned already in mathematical physics. Bessel function is given as in terms of sin for large values of r. So now this equation becomes, this is equation 1, this equation becomes, so instead of JL of kr, you will have to substitute this expression. So you will have the total wave function is nothing but this expression. So what you have done, instead of JL k of r, kr, just substitute this expression plus your scattered wave. Okay. Now sin kr minus L pi by 2 by kr can be written in terms of exponentials. So we know already this one, which can be written as e power x minus x divided by 2y. So we know already. So e power kr minus L pi by 2 minus e power minus kr plus, okay, IL pi by 2 divided by 2y. Now I can write this as separately, e power ikr e power minus L pi by 2 minus e power minus ikr e power IL pi by 2 divided by 2y. Okay. Now I am going to simplify this term alone, e power L pi by 2 e power IL pi by 2 like this. E power IL pi by 2 can be written as e power I pi by 2 to the power L. So we know already this, correct? And this e power x can be written as cos x plus I sin x. Okay, e power x can be written as cos x plus I sin x. Your x will be I pi by 2. Okay, so cos I pi by 2 plus I sin I pi by 2. What is cos pi by 2? Cos 90, 0. What about sin 90? 1. So you will have only I. So I to the power n. So that will be your assignment. You just try. Okay, assignment 2. Similarly, you can go for e power minus x. E power minus x can be written as cos x minus I sin x. So you will have exactly minus I to the power n. So e power IL pi by 2 is written as I to the power L, whereas e power minus I pi by 2 to the power L can be written as minus I to the power L. And of course multiply these two, I minus I to the power L, I to the power L, which is nothing but e power x multiplied by e power minus x, which is nothing but 1. So we can write this. We are going to use this term often, minus I to the power L multiplied by I to the power L equal to 1. Okay, so this sin kr minus L pi by 2 which is equal to minus I to the power L. So instead of this, okay, instead of this you can write minus I to the power L, then e power ikr minus I to the power L, so which is nothing but your I to the power L multiplied by e power minus ikr divided by 2. Is it okay? So this term in the wave function, this is the wave function. So this term in the wave function can be simplified as in the exponential term as exactly like this. Okay? So now we are going to replace. So this term is replaced as this term. Is it okay, everyone? Now look at this term with a minus sign. So we can have separately, we can write this equation. So this equation contains one part, this equation contains another part. I am going to separate with a minus sign. So minus sign exists. So one will have positive sign, another one will have negative sign. So I am going to separate the first term into two terms. So I have separated. See? So this term, you just look at this term, exactly this will be a first term. Okay, minus I to the power L e power ikr. Look at this term with a minus sign, you have minus sign I to the power L, I to the power L. Okay, you have I to the power L, 2L plus 1. Here I to the power L, e power minus ikr divided by 2ikr, 2L cos theta. So I have separated the first term into two terms. Okay, and just for the simplicity, I can write this as minus term here and plus term this side. It means you compare the first term and the third term. You just compare the first term and third term. E power ikr divided by r. Here also you have e power ikr divided by r. So you combine first term and third term and you can write e power ikr by r common out. The remaining term. Here the remaining term will be f of theta, comma phi is constant, so f of theta plus this term. The second term is, let it be like this. So you have minus term which is nothing but the second term plus you pull e power ikr, both the terms are common, e power ikr by r out, the remaining terms. This is very important equation. Just remember this equation for the time being. Okay, you remember this. We are going to compare with the another solution. Okay, so we are going to use 6.109 later. Is it okay? So now we have minus term, this term, and we have plus term. So we have combined first term and third term and we have written here. Second term, let it be like this. So remember this 6.109 equation, just remember. Okay, now asymptotic of radial function, when r tends to 0, we know that v of r equal to 0, we know already. Okay, we learned in the last classes minus e squared by 4 pi epsilon naught r. So when r tends to 0, your v of r will be 0, we know already. When r tends to infinity, v of r will be 0. So we know already. Okay, now equation 6.97, this 97 becomes, for L equal to 0, for the ground state, this equation becomes exactly like this. So we are going to have now complete radial function. We are going to use spherical Bessel function completely. I repeat, we know already this, and this equation we know already. This is for the radial part. R tends to infinity, your v of r equal to 0, so this term will go off. L equal to 0, for the simplicity, for the ground state, this term will go off. You have only these two terms. Okay, is it okay? For the ground state, the solution of this equation is nothing but Bessel function of the first order and second order. The complete solution of this equation for the radial part is nothing but Bessel function of the first order, Bessel function of the second order. Usually first kind and second kind people will say. So this is termed as Bessel function and this is termed as Newman function. Again, which we learnt in mathematical physics, okay, about Bessel function. So this is the combination of Bessel function and Newman function will be your complete the solution of radial part of this equation 6.110. Is it okay? So this is your Bessel function and this must be your Newman function. So asymptotically, the Bessel function is expressed as this. We have already seen in terms of sign. Asymptotically, the Newman function is expressed in terms of cos. This is in terms of sine. This is in terms of cosine. Okay, cos term with a minus sign. I repeat, we know already about the solution of Bessel function which is in terms of sine. We learnt already. Okay, and also we know that this must be Newman function is expressed in terms of cosine function when r tends to infinity. So now together, you substitute in this equation, complete solution. So that will give us equation 6.114. So this is your Bessel function, this must be your Newman function. So this is a complete solution. Now we are going to introduce two terms which is very important, CL and del L. CL is a constant and del L is a phase factor. Suppose we are going to introduce all the terms. So we are going to have L equal to 0, L equal to 1, 2 goes on. We are going to have all the mixture of spherical waves. Surely there will be a phase factor. Surely there will be a phase difference will be there. So we will have to introduce, surely we will have to introduce no other way the phase factor. So which is nothing but your del L. So which is given as AL equal to CL cos del L, DL equals minus CL sin del L. So AL is termed as like this, DL is termed as like this. And for the magnitude, we just to square it, you will have CL equals root of AL square plus BL square. Divide these two, that will give you phase factor tan del L, which is equal to minus BL divided by AL. So phase factor can be obtained as this expression. Now substitute here.